So there's a couple of chemical substances. One is iron nitrate. So I picked iron nitrate because it's got a nice color. We could have done chloride as well because we know it's chlorides in the ocean, but that's fine. So we're going to have transfer that into our beaker. We've got a delivery tube here. So the thing with delivery tubes is that you can seal the delivery tube and allow a gas that's produced to bubble out. And that's what we're going to do. So what we want to do is to bubble that through our solution of iron and see if we can precipitate. That's the plan. Right? Now, we do that because when hydrogen peroxide decomposes, breaks down, it turns into what it looks like water, it turns into water, so you can't really see anything going on. And it also produces oxygen. So, and that's what we want. So when this decomposes, it releases oxygen gas. So the oxygen gas that it releases is what we are wanting to do. So when we pump oxygen into the solution, hopefully we will see some red bed formation. So what we want to do first of all is we want to transfer probably most of one of those bubbles into our beaker.
That's how much one bottle contains. That is not a lot.
That's not much. So what we might do is we might just add some water to that. What we want to do is we want to actually liberate some gas from the hydrogen peroxide. So we're going to transfer some of that. So they might go, is there a test tube rack under your bench? So now what we're going to do is we're going to transfer about, nuts. Not quite sure how nuts. So maybe that, yes, that would be a beautiful. So this is actually decomposing now. It's breaking down, but it's a chemical reaction that's so slow you can't really see it. So what we do is we speed it up, and we use a substance called a catalyst to speed it up, which basically makes things react more quickly than they would otherwise.
So is it also breaking down in the bottle?
Here? No.
Did that?
Oh yes, it is. Yes, that's right. So that's why these things only have a certain life.
That's what
as
this
well.
is for.
They will die after a while. So what we need is we need something to help this react quicker, because if we wait for the oxygen to be produced from here, we'll be waiting all day. So we're going to put a little scoop in there, but we need to do two things. Firstly, we might bring this over. So we need to make sure that the oxygen that's produced is in the water. Because what we're doing is we're modeling the oxygen production of the cyanobacteria. So they were releasing oxygen into the water, which was creating these little red beds. So we can even bring it up a little, so it's kind of shallow water rather than deep water. Now, the important thing is once we dump that in, we need a stopper.
Will it not go?
Because otherwise it will come up. So we don't want it to come up, we want it to go in there.
Oh. My hand twitched. I will clean that up.
That's all. All right. Okay. So
That much?
yeah, probably a little bit less than that. Okay, beautiful. Here we go. Up on. Okay. Now, see the bubbles? I've got some bubbles, so that's nice. Can you see the bubbles?
Yeah.
Beautiful. Okay. So it's bubbling quite nicely over here. So that's the production. So this is the production of oxygen. Now, when you have a really concentrated peroxide solution, it comes up super quick. Now, we don't want it to come up that fast. We actually want the reaction to be quick, but not so fast that it ends up going everywhere, because we don't want to. We want to try and see if the addition of this oxygen is actually going to do anything to our iron solution. So what are we noticing at the moment?
Bubbling.
we've got bubbles, okay? Now, initially too, this was in air. So the first few bubbles, when it's pushing out, is pushing out bubbles there. Even though it's generating oxygen, it starts by pushing out, just clearing. It's basically like clearing all the air out of the tube at the moment. So now what you should have is virtually pure oxygen that you're producing. That's now filled the tube, and also this. You can breathe that in. And what we're trying to do is we're trying to look for a couple of things. One, can we see any change that's happening to the colour of the solution? Secondly, to see if there's anything, yes, this one it's definitely changed colour. Settling a little. Okay. So we'll make that once the bubbling settles.
If you take the cap off, will it just stop? Or
No, but what will happen is that the gas will then escape from here, okay, rather than bubbling through our solution. So you can see the bubbles are slowing down now. So we've made a model, and in our model, we have iron in solution. We also have water, and then we have oxygen bubbles coming through. Is there any aspect of the early ocean? So what's our problem? The oceans were slightly acidic, so we're going to need to add a little bit of acid to see what's happening. Now, obviously, we also have killed our plants because there's no more oxygen. So we're going to have to do two things. We're going to try a little bit more of so the reason there's no oxygen is one of two things. The catalyst is no longer active, or we've used all the peroxide. So we may put a little bit more of that powder in there and see if we get more bubbles. If we don't, then we just add a bit more of peroxide, okay? But I'm going to go and grab some acid just to see if we can acidify it a little bit. There's a little bit of hydrochloric acid here, which we're going to add in. Just look at the edges of the organ. So the colour was really pale, and now it's looking like it's getting quite dark at the bottom. Can you see that?
Yeah.
That's beautiful. That's a banded iron. So actually, I think what's happened is that when the Orbi was in there, it was actually drawing the precipitate out. So it was kind of sticking to it. And now that we've taken it out, you're starting to get a little bit more stuff happening down here. So which means that we can probably add a little more. It's still bubbling, so it's probably okay. I don't know if you're close. If you go down and have a look at that, you can almost see the layer forming at the bottom. Can you see that?
Oh yeah. If we run enough iron one day, could we just make big chambers of this and get iron on it?
Well, there's one way that we can do this. Did you see that? Could you see that, Caleb?
Yeah, I did think so.
It's just
The little red bits, layers at the bottom.
It's just a little slightly darker layer on the bottom that we're getting. I don't want to kind of stir it up too much. But it's just starting to settle at the bottom.
Yeah.
And that's a red bed. That is a banded iron formation. So I'm pretty impressed with that. Now, I don't think we got that with the without the acid. So I think that it was necessary and this is one of the things when we talk about modeling, we weren't there in the early ocean, so we don't know what they were like. we're trying to sort of guess some things about the conditions. So what we do is we play around with the chemicals to try and recreate some things that we think might have happened. Now, obviously, we're creating red bands in a very short period of time here, and we would expect that that would take longer and be much slower to form. But you can see, just with what's happening here, we're pulling some of that iron out. Potentially what we could do is remove all of the iron. Now, the other thing that the iron, you can see that what the iron does is it changes the color of the solution. And as it's pulling that iron out of the solution, we should expect to see the color dropping and the concentration happening down the bottom. There's definitely a layer on the bottom. You see that? There's quite a distinct layer on the bottom, which is what we're trying to do here. When we're doing a method that's designed to help us model a process, and when we're looking back in time, particularly when we're looking back, these red beds are like 2 billion years old. They're like ridiculous age. It's almost nonsensical because it's so big. If you want to model something, if you want to try and sort of figure out how something happens, you're trying to recreate something that you don't know. So it means we're trying to sort of build something that we didn't have previously. And so what I'm thinking that we might do with this is we might let it sit and settle, and over the time that it settles, we might find some of that solid actually comes in. Have this program called Risk Assessment. It's a really good program because it allows us to identify specifics about the sorts of materials that we're using. So when we ask you to analyze risks associated with practices these days, we want you to think specifically about stuff. So, for example, we use glassware. Now, you can include glassware as a hazard or risk, but we drink out of glasses. So glass itself isn't a hazard. What is a hazard associated with glass?
The broken glass.
Yes. So if the glass breaks, then it's a hazard. Okay. So broken glass would be the hazard. The potential is that obviously you could cut yourself potentially quite badly. So we handle glassware carefully and we clean up any breakages quickly, so they're not sort of left lying around. So that's part of what we want you to do with your risk assessments now, is that you're looking at equipment and also chemicals specifically. So here's hydrogen peroxide. I can do a quick search here. If the thing pops out of the way.
Would that be poison?
Now, you can see what's here. Now, we've actually used 3% today, which is why the reaction was very slow. So we've used 3%. Here it is. Potential hazards, low toxicity, can be poured down the drain. So would you consider that the hydrogen peroxide that we've been using to be safe?
Yes.
Okay, so will it go in our hazard?
Yes.
Possibly, but
Drink it.
well, let's have a look at a higher concentration one. Yeah, so one of the assumptions that we're making is that we're not necessarily going to put every single thing in our mouth.
Yeah, but
In a science lab.
but
All right.
others are-
Now, here's what happens. If the concentration of hydrogen peroxide is higher, it's corrosive to eyes and skin. It can produce white blisters on your skin.
Ooh.
Sealed bottles can explode due to the buildup of oxygen. And it can have some quite significant consequences. So hydrogen peroxide is a hazard, but we're using such a low concentration, we're using it in such small quantities that it's safe. Okay, so you can identify hydrogen peroxide as a hazard, but you can say, so the potential, potential for harm is that it can irritate your eyes and your skin, but our control measure is low percentage. okay, or low concentration. So when you see those more explosive kind of elephant toothpaste experiments, they're using probably 15%, something like that. So it reacts much quicker, and it's just a little bit more dangerous to work with. So what else have we used? Well, we used iron nitrate. Okay, and again, we used a 0.1 molar solution, so we're here. All right. So iron nitrate. So that's what we also used. You can see in the hazards, it could irritate the eyes and the skin, but we can dispose of it down the drain as long as we use. It says a stream of water, so that means we don't just pour it down the sink. We kind of rinse it as we do it, so it works okay. So what I want you to start doing is when we're doing these sorts of experiments, there's a sheet here that has a little table with hazards and the potential for harm and the control measures. So again, we've used a very low concentration. So you can see that what we've used is between 1 and 3%. So they're very low concentration solutions. So we've done that deliberately, so they're not going to be a problem for us. We can play around with them and they'll be fine. Now, one thing which you could, which I'm just going to change here, is we can also look at the product of what we produced. Okay, so when you produce a solid, obviously, if the solid is very fine, you could breathe it in. Now, the solid that we produced is relatively fine, but it's in solution. So, I mean, unless you stick your nose in there, you're not going to breathe it in. All right. And again, we can kind of dispose of that fairly safely. So this is what we're talking about when we're talking about hazard management. Is what we're trying to do is identify something specific about the chemicals rather than just saying don't eat chemicals, wear your safety glasses, because Year 7 would tell me that. Okay, so what we want to try and do is to look at the specifics of what we're using. Sometimes we use small quantities, sometimes we use very dilute solutions, small percentage rather than high percentages. Sometimes we will substitute things if we think that one thing's safer than another, that sort of thing. Oh, the other one we looked at was potassium. The other one we used was potassium iodide, wasn't it? That was the white powder. But you wondered if it had another name. So we'll quickly do this and then we'll get out of here. And it was solid, potassium iodide solid. So this is why I said don't eat it. Okay, so the potassium iodide is toxic. It irritates your skin and your eyes, or it can irritate your skin and your eyes, and we need to keep an eye on it, okay? Not throw it away in the garbage. So,
if you swallowed it, what would happen?
I don't know. I wouldn't. It says harmful if swallowed. So different people will. Yeah. So we kind of don't want to be swallowing stuff that says harmful if swallowed.
Yeah, but I want to know what would happen. I'm
Well,
not saying I would swallow it. I'm curious.
I don't want anything to happen to you.
I know, but they
care
say
about you too
harmful,
much.
but I'm like, then what do they do? Do they like mess up your insides, or do they just like hurt it there, or it's like,
It's
harmful
all
to
sorts of different,
spectrum.
all sorts of different things that happen. All right, we're done for today. So I'll say goodbye to you. I'll hopefully play around with the little video so that there's some stuff that you guys can get from it, and I will see you guys and maybe you tomorrow.
Yeah.
Cool.